My name is Francis Bitonti. I'm founder of Studio Bitonti. We're a design studio based in Brooklyn, New York, and we focus on design problems that are very material-driven. We do a lot of work with 3D printing, and it's not the next industrial revolution. We don't like using that term. I like to say we're producing designs and material solutions for the information age. I think there's a whole new set of information that's available to us now, whether that's customer data, engineering data, and we can structure materials digitally with software and get new material mechanical properties that we've never had before. The last presentation was an excellent example of that. So I'm going to tell you a little bit how we work in the studio. We don't really have, why is it not? There we go. We don't really have anybody called designers. There's two kinds of people. We either have what we call a design futurist, and the reason for this is that we want people thinking about how the technology is contextualized relative to design. So, it's not just about producing new technology. It's not about producing beautiful design. The question is, how can we be very aggressive about creating culture? So we want brands to be using technology and innovation-driven projects to produce a new kind of human. It's not just human-centered design. We're trying to figure out who we're going to be, and we want to play an active role in making that person and that customer for companies. I want to start off by talking a little bit about form and how we think about form. I started working with 3D printing back in 2007. And one of the things that I noticed very early on was that we were being incentivized to create different kinds of geometries, right? The economic model around 3D printing was pushing me to make things that were very high surface area and low volume, whereas early in my career as an industrial designer, I was being pushed to maximize volume and reduce surface area. The nature of the tools were different. And as a result of that, we were finding new properties and new kinds of materiality that we weren't really dealing with before. The other thing was that because these geometries were so complex, we were having to generate all these material structures by algorithm. When I was a grad student, I studied with a mathematician for a summer. His name was Stephen Wolfram, and we worked a lot with systems like this. And what was amazing about this to me was that nobody had ever generated it. Nobody had drawn this, right? It was something that a computer generated from a simple set of rules, but it looked human, right? It wasn't math art. There weren't easily recognizable structures. There aren't spirals in here. There's things coming together and coming apart in very sophisticated ways. And as a designer, this was very appealing to me. So the first part of my career was really trying to see how I could take abstract, information-driven binary systems like that and use it to drive the creation of geometry and form. At the time, I was working as an architect, and I was doing a lot of formal experiments, and I was producing proposals like this, and clearly architecture wasn't going very well. So we started to kind of change gears and really focus on products, because I realized that the technologies that available to me at the time were really operating at a product scale and a material scale. We were able to do very, very fine manipulations of material, but at that point in time, we weren't really able to do really large-scale manipulations. And again, this was not that I wanted to make a chair that looked like a bush. I didn't want to make a table like whale teeth. We were trying to kind of reconcile a different economy and a different model of efficiency. This was a kind of formal language that I thought was emerging out of the design pressures that I had at the time. Our first commission was to do a bike rack for the DOT. The city was looking for new concepts to encourage cycling in the city. The idea was that we would produce hundreds of these by a computer, and each one installed in the city would be completely different. It was the early days of 3D printing. We 3D printed all of the bike racks. The city wasn't too thrilled because we made a $50,000 bike rack. But they did let us make two of them at the time. One of them was installed at the Cooper Hewitt National Design Museum in Manhattan, and the other one was installed at Astor Place. These are some photos of that early work in the shop. And even though this cost $50,000 at that time, I mean, today we can make this in the studio for a few $100s, right? And it's not an enormous span of time. So the technology is becoming increasingly more accessible and increasingly more effective. This is the one that was installed at Astor Place. So the bulk of our work right now is really looking at materials and looking at how these algorithms not only generate form, but how do they generate new material properties. And how do we start to merge that with design objectives? So we're very often playing the link between engineering and design. This is an example of a reaction-diffusion. This is an algorithm that we might use very often. We're using it in 2 dimensions, and on each axis, we're plotting all the different parameters, right? So this is everything that that algorithm can make. And this could be something that we link back to engineering data, and maybe we have some sort of function that dictates the kinds of forms we create. Maybe under certain loading conditions, we're creating one kind of structure. Under other loading conditions, we're making another kind of structure. But we work a lot with consumer products and brands, and the question often is, well, how do we start to balance these mechanical objectives, these manufacturing objectives, these very serious technical objectives with what we're trying to achieve from an aesthetic perspective, or what are we trying to see from a customer interaction perspective? So we can start to cultivate different behaviors from that space of possible designs. This was a project we had done. Well, this isn't a project we had done. This is an MRI. But I like to show this to lead into this project because what you're looking at are cross-sections through a human body, which has a variety of different material densities. There's bone in here. There's all kinds of other fatty tissue. There's organs. But what's interesting for me is that every pixel represents a different material property, right? We're taking something from the physical world and we're encoding it digitally. And we could use that to isolate different structures and different materials. But we could also go the other way. A few years ago, we were working on a handbag, and Stratasys was just starting to release this multi-material technology. And a handbag seemed like a good multi-material problem for us, but we got stuck right at the hinge. The hinge was falling apart. It was flaking. The rubbers weren't what we thought, right? These materials on a kind of micro level were not behaving the way we were used to. So what we ended up doing to make that hinge, let's see if this plays. So what you'll see here is just static, right? And what you're looking at really is what we fed the machine, right? So each one of those little pixels is a different material. Black is a soft, flexible rubber. The white is an ABS. And we blended between those two to create a composite that would be reinforced and strong enough that we could use it as a functional hinge. And this got us thinking, well, maybe we could produce very graded optical properties as well as mechanical properties. This was a test part that we had made that includes both a clear acrylic and a very flexible, soft black rubber. And again, what you'll see in this video is a series of cross-sections through that object, and you'll see everything from white to red to all shades of pink in between. And all those different shades of pink are actually different microstructures or different depositions of those two materials. And we're using that deposition of materials in order to create things that are either optically graded, going from clear to opaque, or functionally graded in a mechanical way, going from a rubber to a hard acrylic. These are some results of the output. You can see some variation in material. There's no hard lines between the parts that are kind of, you can see those little halo effects where it's clear versus opaque. Here, this demonstrates it very well, right? There's no assembly here, right? But we're getting all these different materials and different properties, and we're continually blending from one to the other. This can be used to create articulated skins. We've used this to create color gradients for shoes. We've also started applying this thinking to really kind of basic desktop printing. Thinking about the set of printing structures as a field of vectors. Why is this not playing? Sorry. So we can create very small vibrations in the nozzle. We can change the feed rate. We can change the extrusion temperature. We can change all of these things that are forming these thermoplastics at a micron by micron, well, tens of microns at a time. So we can produce. We could take a shoe that might be 20, 30 components and start to get that functionality in 2 or 3 components. These are some early tests. We've also, for this company, this is a startup, their name is Feats. They're going to be launching in DSW stores later this summer. We've built software for them so you can generate these shoes on the cloud from foot scans. You'll generate all the machine code directly, which will produce all these different properties based on the customer's needs. And directly server side. This machine is produced, made in their factory in San Francisco, and will be shipped to the customer. These are some of the first products that are going to be going to market. We've done the same thing to create textiles. This is a collaboration we did last year with Intel and Chromat. We engineered the mechanical moving fan on the back of the model, but we've also 3D printed the entire textile. And what you'll notice is that it looks like a very fine mesh or a weave. That comes from us being able to control the directionality and flow of the material as it's coming out of the printer. So we can give it a stretch or a bias in certain directions, depending on where we wanted it to have give. This is another project that we're probably most well known for. It was a dress done for burlesque icon Dita Von Teese. The dress has 3,000 mechanical moving parts. And what's cool about this is that they're all unique. So there's no two parts on this dress that are exactly the same. The textile was made exactly for her body. It was generated in 3D from, if you think about it geometrically, like a Chinese finger trap, a bunch of spirals wrapping around her body, and we used that to generate a textile that was 3D printed. The question I get asked a lot is, well, how do you make 3,000 unique mechanical parts? You can't, right? So we had to come up with a system of mirroring and tiling and stretching and distortion in order to map each one of these components to her body. About 12 panels or swatches of textiles were generated to be 3D printed. They were finished, dyed, lacquered. 12,000 crystals were applied to it.
Okay, we have the first
kill the audio?
batch of the dress coming through.
The audio? Shut it off. Thank you. This is how it comes out of the printer. So you can see it when it's done, it's printed, it comes out fully articulated and flexible. Nobody had to go and assemble all of that chainmail. It was assembled in the printer. The dress is very, very light. It's only this is 0.5 millimeters thick. It weighs 10 pounds fully assembled with a corset underneath, which is only about, I think it's 70% lighter than what Dita would normally wear on stage. And you can see here the dress flows and it moves very much like a fabric. The shoulders were kept rigid, and we draped the fabric off of the shoulder structures. This was done in collaborations with the Hollywood wardrobing studio in Los Angeles called Michael Schmidt Studios, and it was showed at Fashion Week 2012, I believe, at the Ace Hotel. So detail of the shoulder. So I like to spend a little bit of time in talking about consumers. Like we talk about what kinds of materials we can create. We can create functionally graded materials that are changing and doing all kinds of things. But could we also use these algorithms to create new design interactions or interactions with the customer? Can we kind of rethink customization a little bit? I'm going to show you 3 simulations. Each one of those simulations is the same algorithm. This is what you would use if you were making a Hollywood film to simulate a flock of birds. We've constrained those agents to a 3D scan of a model. You can see in this simulation it's clothing very close to the body. In areas where there are less curvature, they settle into spirals. They move out of areas of high curvature very quickly. Changing one parameter, we're going to get a completely different kind of behavior, right? Now, in areas of high curvature, the agents will leave the body. They'll start to spiral. As this simulation plays out, you're going to start to see structures very similar to a skirt starting to emerge. It's the same system, the same code. It's just one detail changing. So we apply these kinds of systems to products. I mean, that's a much more abstract situation. We used it to create a pair of shoes for United Nude last year. We did a limited edition of 8 shoes for United Nude. Each one of the heels are generated by a computer application, and they're generated for the person who buys them. So there will never be more than one of the same structure on those heels. They're 18 karat gold. They're plated. It's not solid gold. The upper is a cow skin. So you can see it's a very complex, very intricate structure. this shows some variation in what that algorithm is able to produce. And if I let this video play out, you'll see how we can progress from something that is very linear, lots of straight lines and ribs, but as it plays over, you're going to start to see this knotting of space, right? It'll start to become more tangled and more cavernous, and it'll start to take on a different characteristic. We've applied this to jewelry. You can see here a range of, why are we stuck? Things from very ordered linear curves to more knotted kind of textured curves. Just to close, I want to close on just thinking a little bit beyond materials and customization and form, and thinking, well, what do these technologies as they progress maybe mean for manufacturing? We're in this room, there's a lot of big industrial machines, there's also a lot of desktop machines, and a lot of those desktop machines not long ago were large industrial machines. We're seeing a larger and larger network growing of makers, of small fabrication facilities, even very large fab labs. So the question I have is, well, as that becomes more and more accessible, what is that going to mean for how our products are distributed? This is a map of the 3D Hubs network. It's pretty old right now. These were the top ranked hubs in 2012. There was only 5,000 printers on that network. Today there is over 30,000 printers on that network, so this map would look much different now. We wanted to see if we could use this network to release limited, like an edition of goods that would be customizable, but where they would be produced and sold by the local hub. So what we did was we would take the customer's zip code, their name, and we would file that all away when they put the object in their shopping cart. After they made the purchase, we would use 3D Hub's API to send all the information to the local hub. The local hub would process the order. They would set their own price. We would only sell the digital file back to the 3D Hub, to the local hub. So we were trying to produce a kind of local economy and letting these hubs sell and distribute their own products. All the pieces were designed to be printed on desktop printers with no post-processing. We didn't send any STL files. We only sent machine code. You can see they're fairly complex geometries. We're really right on the edge of what can be produced at home. And that concludes my talk, and thanks for your time.
Francis, thank you.